In this video, I'm going to be doing a quick revision of test 1 in anticipation of the exam. So we're going to be doing this in its entirety. As you can see, it's from 2025 and it's set by our professor, as you can see here. So let's start with question 1 without making the intro too long. So I'll start with 1.1. If you already know the definitions and how to define these terms, I think you can comfortably skip this section, right? You can comfortably skip this section, but I'm going to define them so that, I am able to remember them when the time comes. So basically, the first one here, a space lattice, is defined as, so we're going to say 1.1 here. Where is my pen? I'm just going to say 1.1 here. And then number A, space lattice is an infinite array of discrete points in space that are arranged in a regular and periodic manner and have the same or equivalent surroundings. Number B, which is inversion symmetry. If you remember, the definition of symmetry is defined as a natural occurring of phenomenon that implies proportionality and regularity resulting in beauty. So this one is inversion symmetry, and it's defined as, you can say, is the reflection of an object in all axes through a point called the center of symmetry, like this. And then number C, it was what a basis. You remember that a crystal structure is made out of a basis plus a lattice, right? So you can say a basis is a group of atoms that, when placed at lattice points, generate the crystal structure. So basically, on all definitions, SPHA will allow you to define them in your own words, as long as you explain the same thing, right? Can define them in any way you want. So let's skip to the second question. So basically, the question says copper crystallizes in a CPP type structure with a density of 8.9 grams per mole. The Avogadro's number is given to us as that. Use the information in the periodic table to calculate its atomic radius based on the hard shell model. So to answer this, you must first know that CPP is closely packed, right? CCP closely packed, so you must know that CPP is equals to FCC, right? So these two are the same thing. So basically, our CCP here. So basically, what we must know is CCP is equals to FCC, right? These are the same thing. That's the first thing you must know. And then you must know the formula for density and how to use it. And you must also know how to relate the radius, right, to the formula for density, right? So we can say that density is given to us by the number of atoms multiplied by the atomic weight divided by the volume of the unit cell multiplied by the Avogadro's constant, right, like this. So this is our formula. What we need is going to be radius. So as you can see, there's no radius in this formula, but we do have volume here, right? And the volume of a unit cell that we can relate to A, right? So we can say VC is equals to A3, because you remember that if we have a 3D object and want to measure its volume, we can multiply. Let's say we have a 3D object, right, like this, right? To get its volume, we multiply this side by this side by this side. So if this is A, this is A, this is A, we get the volume of the cube is equals to A3, right? But we know that our object is FCC, right? In an FCC structure, we can say the following, right? FCC structure. In an FCC structure, we know that we have atoms at the corners and we have atoms at the faces, right? So we can take a cross section of one face and we can draw it like this because it is the most closely packed. That's why we're using a face, right? We're gonna have an atom here, and we're gonna have an atom here. We're gonna have an atom here. We're gonna have an atom here, and we're gonna have an atom here. Remember that this is 100, right? This is this face. This is this plane here. And in here, you remember that this is A and this is A, right? What we can do here is do this, right? Have a diagonal line there. If we say that the diagonal line is x, we can say that x squared is equals to what? A squared plus A squared, right? And then we can say S squared is equals to 2A squared, right? And then we root both sides. We can have x is equals to the square root of 2 multiplied by A, right? So this diagonal side here is equals to that, right? But you will notice that in this diagonal side here, which is the most closely packed side, that's why you are taking it. Our length is given by this, but our radius, which is what we're looking for, is given by these atoms here. We know that a diameter is made out of 2 radius, right? So in here, we have the entire length for this atom. So we're gonna have 2r here, which is r and r, right? But on this atom here, we're gonna have r, and in this atom here, we're gonna have r. So 1, 2, 3, 4. We have 4 radius here. So we can simply say that 4r is equals to the square root of 2 multiplied by a, right? And to get r, we simply divide by 4. So we have r is equals to the square root of 2 divided by 4a, right? So we have our radius here. This is the formula for our radius for an FCC structure, right? So basically, we need to substitute this r back into that, right? Oh shit. I think I made a mistake. Oh. So basically from here, what we can do is isolate A so that we can substitute it back into this formula. And then we substitute this back into that, right? So we can say that our A is going to be 4r, right? Divided by the square root of 2, right? From there, we can substitute this back into that formula. So VC is going to be equals to 4r divided by the square root of 2 cube, right? This is going to be our VC. From there, we can now solve the problem, right, that we're given. We have planar density is equal to the number of atoms multiplied by the atomic weight divided by the volume of the unit cell multiplied by the Avogadro's constant, right? So to get the number of atoms, we go back to our FCC structure again, right? In an FCC structure, we have 8 atoms, right? We have 8 atoms at the corners. If we multiply those by 1 over 8, because they contribute 1 over 8, we get 1 atom, right? Plus, we have 6 atoms at the faces, but those contribute 1 over 2, right? And we are going to get 3 out of this. So in total, our n is going to be equals to 4, right? N is going to be 4. Our n is going to be 4, right? So for our atomic weight here, we just check the periodic table. We're given copper, right? If we look at the periodic table for copper, we are going to see that the weight of copper is 63,546 grams per mole, right? And we know that our density here is given, and also our Avogadro's constant is given. We've already determined our volume. So what we're going to do is make that the subject of the formula. To do that, we simply multiply this by this, or cross multiplication. We can get our volume is going to be NA, and then we can say PNA, right, like this. But now we can substitute this one here. We can say 4R divided by the square root of 2. This is to the power 3 is equals to, here we have 4, right? And then here we have 63, 546 grams per mole from the periodic table. And you remember that we were given the other values here. We were given 8,92 grams per mole, and then we were given Avogadro's constant as well, which is 6,022 multiplied by 10 to the power 23, right? I believe this also in grams per mole. Where is that? That is atoms per mole, okay? Atoms per mole, like this. So we have a value here, meaning this side is covered. But to isolate our R here, what we can do is take this and put it into a calculator. Okay, I can say 4 the square root of 2, and then we cube that. We cube it, and we're going to get 16. Here we're going to have 16 the square root of 2 r cube, right? And then this side, I'm not going to put this into a calculator yet. I'm just going to carry it. 63,546 divided by 8,92 into 6,022 multiplied by 10 to the power 23, right? And then we are going to divide both sides by this term and root everything, right? So we're going to have r is going to be equals to the cube root of 4, right, into 63,546 divided by 8,92 6,022 multiplied by 10 to the power 23, right? And then here we're going to have 16 the square root of 2, right? This is what we're going to have. So all we have to do now is plug this into a calculator. Okay, we have 4 into 63,546 divided by 8,92 into 6,022 multiplied by 10 to the power 23, right? Oh, and then we multiply that by 16 to the root 2 here. Okay, we're going to have 0,122467 1278, right? And you know that our radius is length, so the unit is going to be meter. You can work out the units by cancelling out here, but those should work out to meters. And this is only 4 marks, so it shouldn't have taken us this long, but I was just trying to be as thorough as possible. What we can do is write this and then write this and then skip to here where you substitute this one and then you solve the entire thing and you got and you get your 4 marks, and that's it. Or you can skip all the steps and come here if you know what you're doing, right? But I was just trying to explain how they got to that answer. Okay, next we are going to do 1.3, right? 1.3 is here. Okay, this is our 1.3. 1.3. We are given that in the attached diagram, okay, we're given the following. In the diagram, in figure 1.1, represent a two-dimensional crystal structure. You must indicate the lattice points with X and then draw suitable primitive lattice. Okay, so I'm just gonna import this diagram into our board. Okay. So we have this, right? We have this one. I'm just gonna try to enlarge it a bit so that it's more visible and try to lock it. So as you can see, we are given this thing. We're told to indicate the lattice points. So what I like to do in this one is just like go for the most obvious one. Some people can like go for this one and go for this one and go for this one, but no. Each lattice point, you remember, it must like be equivalent. So if I'm here, right, I must be able to, when I look this side is the same. When I look this side is the same. When I go to the next lattice point, it must also be the same when I look this side, when I look that side, when I look this side, right? Also, if I go here, it also must be the same. So our lattice points are these, right? The bigger ones are the ones I'm going to choose as my lattice points. Like this, like this, like this. So I'm just going to mark all those with X's. And remember, says you must mark all of them. You must not leave one, right? Don't just mark a few and be done with it, or it's not going to give you the full marks. So that handles number A here. Draw suitable primitive vectors for the lattice. Okay, so for the primitive vectors, we know that a primitive vector is a vector from one lattice point to another. So what we're going to do is just go to the corner here, and we can draw those in another color so that they show. I'm just going to take this one from here to go here, right? And then I'm just going to take this one and go here. And I'm just going to say this one is A, right? And then this one is B. It's important to label them to get your full marks. I'm just going to thicken this a bit so that it is more visible. Okay. Next, they say you must give us a unit cell. You remember a unit cell must have like one lattice point, right? It must have one lattice point inside, and it must have the smallest area. So the one that I'm going to pick is this one. I'm going to draw a vector to there, and then a vector to here, and then another vector to there, and then another vector to there. So that's going to be our unit cell, right? We get our 2 marks. And then we will indicate the basis for the crystal. You remember that to indicate the basis, you must first like calculate how many atoms the basis must have. So in this case, we are going to do the following, right? We are going to look at our structure here, and we're going to say we have one atom here, one atom here, one atom here, one atom here. The big atoms at the corners, right? Big atoms. We have 4 of them, and they each contribute 1/4, right? So we're going to have 1. So basically, you know that if in 2D, right, if we were to put another square here, we put another square here, we put another square here, this atom here would contribute to 4 of those things, right? But the small ones here, these 2, we small at the edge, the small atom at the edge, right? The small atoms at the edges, we have 2, and they each contribute 1/2, right? We're gonna get 1 for those. And then the ones in the middle right there, we have 2, right? And those contribute like the whole thing. So we're gonna have 2, right? Meaning we are going to have 4 atoms within that basis, right? So we have two small atoms, right? Oh, we don't have two small atoms. We have three small atoms and one big one. So for our basis, we can draw it like this. We can come to the corner here and we can say that for our basis, we can have 1, 2, 3, right? And then, oh, okay. Our base is going to look like this. We're going to draw something like, we're going to draw it, oh wait, we're going to draw it like this. We're going to start here and our basis is going to be that, right? So if we were to take this one here, oh, I made a mistake again. We have three atoms, so we're going to have this is going to be our basis. We have one big atom and three small atoms. So if we were to take this thing here, right, and put it into the spaces here, into the lattice points, it should give us the entire lattice structure, right? It should give us this entire structure. Okay, so that's my 1.2 or 1.3. Okay. Booyah. Okay, I'm just going to pause the video here and confirm something, right? We have 1.4 remaining, 1.4. But before we go to 1.4, but it's fine. Let's go to 1.4. Let's go to 1.4. We're going to answer the entirety of question 1 and we're going to leave question 2 for the next part of the video, right? So we're going to take our 1.4 here. This is our 1.4. We're going to log it and then we're going to drag the diagram here. So we are given the following. So for 1.4, we are given this here, right? We're given this thing here, right? We're given this thing. Sorry for all the writings on this thing. It's not clean because it's a used paper. I'm sorry about that. So for 1.4, we are given a set of planes here. And they say we must draw all these planes. We have this plane here. And we have these two directions here, and we must draw them in the diagram given here, right? So the first one is going to be this, right? It's going to be, let's say, 1, 3, 2, right? This is going to be our plane, right? Our plane, we must draw this plane. It's 1, 2, 3, right? So we're gonna start with that. 1, 2, 3. 1, 3, 2. Oh, it's 1, 3, 2. Okay, the first one is 1, 3, 2. So what we're going to do is say here is A, right? We're gonna have 1, 3, 2. This is our plane. In order to draw the plane, we must first find the axis, right? To find the axis is very simple. If this was a direction, right, we would just divide by the highest common factor, right? The highest common factor would have been, but since this is a plane, we take the reciprocal, right? We take the reciprocal, the reciprocals, right? So taking the reciprocals here, we are going to get what? 1 over 1, and then we're going to get 1 over 3, and we're going to get 1 over 2, right? these are going to be our axis, right? This is going to be our axis. So our x is going to be 1. Our y is going to be 1 over 3. And then our z is going to be 1 over 2, right? So we can go to the diagram and plot our diagrams here. So what we can do is first label this as x, right? We can go here and we can label the first one here. This one here will be our x, this one here will be our y, and this one here will be our z, right? We have those. Okay, this one is not visible. I think I made it too big. Let's reduce it a bit. Let's cut it down to size. Okay, yeah. I am going to unlock it, and then we are going to make it a bit less big so it fits in the screen. Okay, and then we're gonna lock that again. So basically for our axis, we are going to say this is our x-axis, this is our y-axis, and this is our z-axis, right? So we're going to just say that, give these labels. So if we check back to our plane here, our axis here, for our x, our intercept is at 1 here, right? This is 1. So we're gonna have a vector here. It goes from here to here, right? And then next we are going to say that our y goes to 0.3, right? Which is 1 over. So our y will start again from here and it will go to somewhere here, right? That's going to be our y. For our z, it's going to be 1 over 2. So it's going to go up to half, right? Like this, right? So once we have all our 3, or this one will be 1 over 2, this one will be 1 over 3, right? So basically once we have all this, we can now come in with our red marker and we can connect all the points here to get our, so we can connect that to that and connect that to that. Where is that thing? We can connect that to that and we can have our plane here. As you can see, this is our plane, right? So for the first one, we've answered it. That is our plane. Okay, so for the next one, we have what? For the next one, we are going to have 1, 1, and -2, right? For that one, we can say B here, right? And we can say 1, 1, 2 dash, right? So for this one, to take the reciprocals is simple, right? We're going to have 1, 1, and then 1 over 2, right? This is going to be minus 1 over 2. And remember, these are not like indices. These are intercepts. So here, we're going to have x equals to 1, y is equals to 1, and z is equals to minus 1 over 2, right? So to plot this into our diagram here, we are going to see that we can see along our z-axis, it's negative, right? So we're going to take our origin and move it here, right? Move it to this corner. That way, if we want to move in the negative direction of z, we just move this way, right? So to do this, we know that for the x-axis, we have 1, right? So for that, we're going to go, let me see. So for that, we are going to go this way, right? We're going to have this here. Oh, wait. That's not neat. Okay, I'm going to take this and I'm going to say this is our first, which is y, right? For our x, for our y, we're going to go this way, right? Like this. But for our z, we're going to go downwards, which is in the negative direction of z, right? Because our z is negative. From there, we can take the bigger one here and connect everything. First, we can connect this one to that one over there, right? And then we can connect this one to that one over there. And then we can connect this one to that one over there. Sorry, I don't have a ruler, but our plane is going to be that. Our plane is going to be, this is going to be our plane. I'm sorry, I don't have a ruler, but that's going to be our plane, right? So for the directions, it's a bit different, but it's still the same. We have these two directions here, right? We're given it's 1, 2, 0. Okay, that's number 1, 2, 0. Okay, we're given the direction here. Okay, wait. Let me try to write it just here, the space. We're given direction 1, 2 bar 0, right? So for this one, to get the intercepts is quite different. It's a bit different. What we do, for this one is divide by the highest common factor, right? We divide by the highest common factor, which is the highest common factor. The highest common factor is going to be 2. So we're going to have 1 over 2. We're going to have minus 2 over 2. And we're going to have 0 over 2, right? 0 over 2. So in here, what we can do is the intercepts are 1 over 2, right? And then minus 1, and then 0 here, right? So to draw this direction, we know that in our y here, it's negative. So we're going to move our origin to here, right? Once we have our origin here, we can now say our x will go 1 over 2 like this, right? This will go 1 over 2 like this. 1 over 2 like this. And then in our y, we are supposed to go that way, in the negative direction of y, right? But remember, for directions, we don't go back to the origin. We start at the head of the last vector and we go to this here. And we're going to have this here at 1 over 2, right? So we have this one. In our y, in our z, right? In our z, it remains at 0, meaning we're going to leave that there. So for this one, we can start from the origin there and then go to the head of the last vector like this. And then we can have our direction here, right? This is going to be our direction, right? This is going to be 1, 2 bar and 0. This is going to be our direction. Okay, our next direction is given to us as, let's see, 2, 2, 1. Okay, 2. Oh man. I made a mistake. Okay, another thing here to notice is that our normalized value was at 2, right? And it's in our y. Now it's at 1. I don't know why I stopped here. Okay, let's rewind this. Oh, let's rewind that as well. Okay, there. So from there, we can go take this one all the way, right? Because it's 1x, right? We can take it all the way there. And to draw our vector, our direction, we can take that to the corner there, right? This is going to be our direction here, which is going to be 1, 2 bar and 0, right? And then next, we're going to do our next direction, which is going to be 2 what? 2, 2, 1 with no negatives. Okay, 2, 2, 1. There, we're going to divide the entire thing by 2, right? So we're going to have 1, 1, 1 over 2, right? So these will be our intercepts, right? So from this one, we don't have to move the origin because we are given it as it is. So in this one, we can say in our x-axis, we can draw a vector from here to here, which is our 1. And we can draw another vector from here. We don't go back to the origin to there because that's 1. And then along our z-axis, we are supposed to go to 1 over 2 here, right? This is 1 over 2. So we're going to drag another vector here and like that. So to draw our final vector, we can take it from the origin here, and from that origin point here we can go to, oh, that's not the right size. Okay, we can go to that over there like that. So this is going to be our direction, which is 2, 2, 1, right? Remember, the normalized vectors are going to fill up the entire thing, right? If we normalize a value, it's going to be 1, right? And it's going to take up the entire unit cell. Okay, so for this one, I think it is complete like that. Okay, we move 1 this way, and then we move 1 that way, and then move half. Okay, 1, 1, half. Okay, I think our 8 marks are secured for that one. For that one, our 8 marks are secured. Okay. I think I made a mistake here. 1.5. Okay, for our 1.5, we need to separate our 1.5. Okay, our 1.5. Where's our 1.5? 1.4. Let's separate these two. Let's separate them. Okay, this is going to be 1.5, right? I'm gonna go save code B, and then we're going to say 1.5 and save that one, and we're going to remove 1.5 from 1.4. Okay, open it and crop it. We're gonna remove the first question, the last question, and then I'm gonna save that as it is. I'm gonna go back here and see if it updated. No, it didn't. So what we need to do is remove it manually. So I'm gonna take this and I'm gonna delete it. Okay, let's say delete this one, and then go back here and import our 1.4 and 1.5. Okay, import both these two. So we're gonna take 1.5 to the bottom. Okay, this is our 1.5. It's going to go after all the calculations. Okay, it's going to go here, and we're gonna lock it, and we're gonna take 1.4 here. We're gonna put it, our 1.4 is going to be here. This is going to be our 1.4. and we're gonna lock it here. Okay, so for 1.5 here, let's see, we are at 40 minutes, so we're still within the hour, right? I still have time to finish this exam in the allotted time, which is 2 hours. So in here, what we have, and I'm gonna be faster than this in the exam because here I'm trying to explain what I'm doing. So in here, we are told to determine the Miller indices for plane A and plane B. So for plane A, right here, we can say that for plane A, okay, let's go back to the black. For plane A, right, we are going to do the following. First, we get the intercepts, right? The intercepts along the x-axis, right? We can take this thing here from origin and go here and see. Could that plane doesn't touch, it never touches the x-axis along this line here, right? it never touches the x-axis, right? But if we look at our x-axis, but from this point we can see that our plane cuts there, right? So it's better to move our origin to this point instead of that point over there, right? So once we move our origin to this point, when we go this way, we can see that our x, right, intercept is going to be 1 over 2 there, as you can see, right? That's 1 over 2, right? And another thing is our y, right? Our y, if we go from our origin here that way, we are going in the negative direction, but it intercepts at 1 over 2. So that's going to be minus 1 over 2, right? And then in our z-axis, we can see that our plane is parallel to the z-axis. So this will never touch. If, like, in our Cartesian plane, something is parallel to our z-axis, it will never touch, meaning the intercept is infinity, right? They will intercept at infinity. They will go up to infinity without meeting. So that is going to be our intercept. Once we have our intercept, we can take the reciprocals, right? The reciprocal of x is going to be what? It's going to be 1 over 2. It's going to be 2, right? The reciprocal of this one is going to be, let's say, 1 over 2, right? Minus 1 over 2 is going to be minus 2, right? And then the reciprocal of infinity is going to be, it's going to be 1 over infinity, right? Which is 0, right? And then that's going to be 0, right? So our planar index for A is going to be 2 bar and 0, right? Like this. So for B, right, this is B. Yeah. For B, we have our x-axis, our y-intercept, and then our z-intercepts. So let's look at our B. Our B intercepts at 1, right, in our x. In our y, it intercepts at 1 over 2, right? And then in our z, it also intercepts at 1 over 2, meaning here we're going to have 1 when you take the reciprocal. Here we're going to have 2 when you take the reciprocal. Here we're going to have 2 when you take the reciprocal. We are going to have 2, 2, 1, right? Damn. Okay, this one here, 2, 2, 1, this plane here, right? It reminds me of something that we did here, right? Was this 2, 2, 1? Oh no, it was 1, 1, 2. It was 1, 1, 2. It's plane. Okay, let me see. The green one is which one? The green plane. Oh, the green plane is this one. It's 1, 3, 2. They look surprisingly alike, right? They look alike, but as you can see, these are 1.5 here, right? These are 1.5. We have our Miller indices, right? So let's go to the next one. Let's go to the next. Oh damn, I think I've run out of space. We've run out of space. We can say a new page. Okay, this is good. Create a new page, and for that one we can go to 1.6. I believe 1.6 is the last question, right? It's the last question in this thing, in question 1. So we can move on to question 2 in the next steps. So wait a minute. Okay, we're gonna answer this one. This one is somewhat self-explanatory, right? If you know what the words mean, then you can like explain. So basically they want the difference between these two. So basically what you need to do is just define them. You know that a crystal structure refers to a regular and periodic arrangement of atoms within a crystal, but atomic structure refers to the arrangement of particles within an atom, right? Within an atom, i.e., we can have protons, neutrons, and electrons. Like this. So basically, atomic structure, it's like self-explanatory, right? For a crystal structure, you have a crystal in here, right? It has like atoms inside it, right? But within those atoms, there are also particles, right? So it's sort of a trick question to like test your understanding, but I hope you understand what I've written here. You can explain it in your own words, so I will mark it correctly as long as you are right. For question 1, we are done. I'll see you in question 2.